Oh, it's all black.
Yes. Doesn't that seem strange? Here's a white powder-like stuff, sugar. When you heat it, it turns black.
Yeah. It smells like marshmallows.
Mm-hmm. You've seen sugar spilled over on the stove before.
Yeah.
It always turns black like that.
Yeah.
Now, one of the reasons for that, Tanis, is that sugar is made up of carbon, hydrogen, and oxygen. And the hydrogen and the oxygen are in the same proportion as in water. You know what the formula for water is?
H2O?
H2O, yes.
Yeah.
Here, you want to put that down so you don't burn your... This is one you ought not to try at home unless your parents are around because you're using fire.
Yeah.
We can just let that go out. Anyway, black ends up because when you heat up the sugar, you drive off the water, the hydrogen and the oxygen, leaving the carbon behind. That's when carbon is black. Okay, now let's do the same thing. Instead of driving off the hydrogen and the oxygen with fire, we're going to do it with a strong acid.
Sulfuric acid.
Yes. Ever heard of that?
Well, yeah, a bit, but I've never seen it before. I only know that it's a strong acid, that's it.
Well, it's very strong, so be very careful when you handle it, because I want you to pour about, up to there of the sulfuric acid on top of that sugar in the glass. Okay, go ahead. Very carefully. It's kind of syrupy like, right?
Yeah.
Okay, that should be good. Now I'll move it out of the way. Now, instead of using heat to drive off that hydrogen and oxygen, this time we're going to use this sulfuric acid, which will do the same thing. So what should the end result be after you've taken away the hydrogen and the oxygen?
It'll turn black.
So it should turn black, and it's already turning brown, right?
Yeah, like brown sugar, sort of.
Okay, but wait till it gets a chance to cook a little bit, and then be careful you don't get in the fumes, because the fumes are kind of terrible smelling. Watch, see it's bubbling? What's going to happen to the black if it's inside a glass like this and you give off the hydrogen and the oxygen to form water vapor? It's going to start bubbling. Now at its beginning. Staying out of those fumes, because here comes a sugar snake. That's the sort of thing that happens when you mix sugar with sulfuric acid and burn it with a strong acid. Here, Eugene, have an oboe.
This is not an oboe. This is just a plain paper straw that you drink soda out of.
Right, except we're going to make it into an oboe.
How's that?
Take the scissors,
Okay.
and you do what I do. First, pinch the top flat.
That?
Like that. And then with the scissors, cut off the corners of that flat part at about 45 degrees.
Okay.
And now you've formed two little reeds. See two little reeds up there?
Mm-hmm.
Now you put that in your mouth and blow gently. Try to get those reeds to move. Ah. What's making that sound, by the way?
Well, the air that you blow into this, well, it vibrates the reeds, and the reeds let some sound in and vibrates the sound.
Yeah.
And it comes out.
Wait, hold it a minute. The reeds vibrate,
Yeah.
but that's not what makes the sound. As the reeds open and close, they make the column of air vibrate up and down. That's what makes the sound. Now, you know that the slower something vibrates, the lower the note. The faster something vibrates, the higher the note. So the note that you're blowing is based on the length of the soda straw. Blow through the soda straw, take the scissors. What happened to you? Oh, there they are. And what'll happen if you cut at the same time? Cut the end of the straw.
Well, the sound will be higher because the well, when you blow, the air is kind of slowing down through the length.
Oh, you
So,
think that?
yeah.
Okay.
When you cut it off, then the air begins to move a little faster. And
Close
then-
enough, close enough. Go ahead, blow. Keep going. You're right. Now, if you try this at home, you can practice. And if you work on it, here's what you can do. Listen. Ah, I've missed the last note. Now, there's only one. Yeah, thank you. That's it. It's obvious why this ant is called a leaf cutter. With its special jaws, it can quickly cut off a section of leaf the right size to carry away. The ant itself, or another one waiting below, will carry the piece of leaf to the colony's underground nest. They're so efficient, they've been known to strip a farmer's grove completely bare of leaves in a single night. The way they harvest and carry the leaves away, you'd think leaves are a major part of the ant's diet, but they're not. Scientists who went to South America to study the ants dug into the nest. Inside, they found the ants don't eat the leaves. They use them as fertilizer to grow fungus, and that's what the ants eat. So the leafcutter ants are actually fungus farmers. Here's a secret message that you could have written yourself.
NCA, IELTS, ETU, LT, BHFE.
See, it's a secret because the letters are all mixed up.
Yeah.
And the only way to read the message is to get them in the right order. A lot of codes work like that, right?
Yeah.
Okay, well, the way to get these letters in order is to wrap them around a cylinder. And here's a paper cylinder like this. You want to put your finger in there?
Okay.
Okay. We'll just wrap it a little bit because if you take a look at it...
It's not saying
okay,
anything.
Watch. See this? The letters are beginning to... See here? The letters are beginning to line up. But
Yeah.
they're not going to line up because this is the wrong cylinder. And that's very important.
Oh,
In fact,
okay.
I'll show you the right cylinder. There's the right cylinder right there.
Oh, it's just a rolling pin.
So if you and your friend have a rolling pin, you can send messages back and forth.
Yeah.
Let's see why this one didn't work.
Okay.
I'll put this one over the top. What's the difference in their diameter?
Okay.
What are you doing with your little fingers there?
Well, we learned in school that this is a centimeter, so I'm
Centimeter.
measuring it.
You're measuring it.
Yeah.
So it's
2
2 centimeters difference, right?
Yeah.
In the diameter. So what's the difference in their circumference?
6.
6?
Yeah.
How did you arrive at that?
Well, I multiplied the diameter times pi, which is the circumference.
That's how you find the circumference of a circle. But what you did is you multiplied the difference between the two by pi.
Yeah.
So you found the difference in their circumference. Very good. Now, as long as there's 6 centimeters difference, each of the letters, if you wrap it around, this one's going to be 6 centimeters off.
Yeah.
So the diameter of the cylinder makes all the difference in the world. This is the right cylinder. You want to hang on to the handle over
Sure.
there? Now you'll get the real message. Now, see the letters are lining up properly?
Yeah.
You see some of them?
At, meet, at, club, meet at club, meet at club, add.
This technique was supposed to have been used by Roman generals, and they sent messages back and forth, and each one had the right size cylinder, so only they could read the message. I don't know whether that's true or not, but here is the message.
Meet me at the clubhouse at 5 Lila.
Christian, here are 6 little figures, all of different shapes. Have you had solid geometry in school yet?
Not very much.
No. You've had regular geometry?
Yeah.
Circles and squares and things like that. Well, these are all different figures. Do you know the names, first of all? What's that one?
Cylinder,
Yeah. And next?
cube,
This one?
a cone,
That one?
Sphere.
Yeah. This one?
A rectangle.
Well, a rectangle is a two-dimensional figure, right?
Yeah.
So this part of it is a rectangle. So call it a rectangular solid. And finally,
Okay.
this one?
Pyramid.
Four-sided pyramid. Pyramids come in three-side, four-side, five-side, six. This one would be four.
Okay.
Okay, my question to you is, how are all these miscellaneous-looking figures alike?
Well, they're all shapes.
By that you mean volume. They all have volume. They're
Yeah.
all, okay, fine. Next.
Well, they're all the same color.
Right, same color. I think probably they're all made of the same material too, right? Plastic? Yeah. Anything else?
No.
Okay, which is the biggest one and which is the smallest one?
Well, I think the rectangular solid.
Is which? Bigger or
Biggest,
smallest?
biggest.
Think that's the biggest. Okay, let's put that one over here. How about the smallest?
The sphere.
The sphere. Okay, now do you know how to find out? They're kind of tricky. You could use mathematical formulas for each one of these to find the volume. But have you ever heard of Archimedes?
No.
Well, he was a Greek philosopher and mathematician, and the king gave him a problem. He said, Archimedes, somebody just gave me this crown. It's supposed to be solid gold. I want you to tell me whether it's solid gold or not. And so Mr. Archimedes went back and he kept thinking, how am I going to tell whether it's solid gold or not? He knew the weight of gold, but he had to figure out the volume of the crown.
Yeah.
And here the crown has got all kinds of peaks on it and everything else. You know, it's pretty hard to figure out the volume. And then, according to the story anyway, he went to take a bath. And when he sat down in the bathtub, he got the idea. And he got so excited about it, he supposedly ran down the streets back in ancient Greece with a towel around him yelling, Eureka, Eureka, I have found it. And what he had noticed is when he sat down in the bathtub, that the water level went up. Obviously, you know, as you sit down in the tub, the water goes up.
Oh.
So he got the idea that all he had to do was put the crown in a fixed amount of water, mark the level, then put the crown in and see how far up it went, and then he'd have the volume of the crown.
Wow.
So that's how we can find out the volume, see whether you were right, whether that's the biggest or the smallest, because here I have 6 little glasses, each one filled with an equal amount of water. So all you have to do is take the first one and put it in there. Okay, now it went up a certain volume, right?
Yeah.
That was, you said, was the biggest. Try the next one. Here is the one you said was the smallest. Okay, take a look. What's the level like?
Uh-oh.
Matter?
I think they might be all the same.
Why? Because those two are the same?
Yeah.
Well, here's the cube. Try that one. Pyramid. Cylinder. Finally, the cone.
They're all the same.
All exactly the same, yes. Well, this group of solids have been designed that way. They were made that way so that in spite of the fact that they're all different shapes and sizes and whatnot, they're not really. They're all exactly the same volume, and you can find that by putting them in water, right? So the next time you take a bath, take a look at the water before you climb in the tub, and then when you sit in it, up goes it, and think of Mr. Archimedes and his very useful principle.
Wow.
When there's a violent eruption of a Hawaiian volcano, molten lava from deep within the earth spews forth with awesome power. As the hot lava works its way to the surface, gases that have been under tremendous pressure are suddenly released. The lava is blasted into the air. Remember, this is rock. Heated to as much as 2,000 degrees Fahrenheit, the rock becomes a thick, gooey fluid that pours out of the vent and collects within the crater. This lava lake is as deep as a football field is long and contains millions of cubic yards of molten rock. Occasionally, spectacular fountains leap high into the air. The highest on record was 1,900 feet, 1/3 higher than the Sears Tower, the world's tallest building.
The lava forms rivers of fire as it pours down the side of the volcano. In spite of the thickness of the molten rock, it can reach speeds of up to 20 miles per hour. Whenever groundwater gets into the plumbing of the volcano, huge clouds of steam roar into the air. The pattern of the eruption can change abruptly and is unpredictable. At the edge of the lava flow, the crust-covered molten rock engulfs everything in its path. If the lava reaches the ocean, the island gets a new shoreline. The U.S. Geologic Survey maintains a scientific observatory on Hawaii to monitor not only the eruptions, but also the day-to-day activity below the surface between eruptions. The information they've collected over the years makes possible more accurate prediction of one of nature's most awesome spectacles, the eruption of a volcano.
Heather, I assume you like apples.
Yeah,
Okay, here, have a piece.
thank you.
Okay, now swallow it. You swallowed it was a little big, I think.
Yeah.
Okay, we'll chew it up a little better, because I'm going to give you another piece, because I wanted you to pay attention to what happened when you swallowed. Did you notice? How many times have you swallowed something?
1,000 times.
Yeah, lots of times, but you never really paid too much attention to it. Here's another piece, a little smaller.
Okay.
This time, at the same time that you swallow, I want you to take a breath. Like that.
All right.
Try it.
It doesn't work.
No, can't do it.
No.
No. Inside of your throat, there's a sort of like a little trapdoor. And when you swallow, that sends signals up to your brain. Your brain sends a signal out to your breathing apparatus and says, don't breathe, stop, until you finish swallowing, so that you can't breathe and swallow at the same time.
That's neat.
Yeah, it's a pretty good idea, too, right? What happens if you get food in your lungs?
Well, you'll be in serious trouble.
Yes, you might cough, and it could be all kinds of problems. So, how does the food get down to your stomach, then, after you've swallowed? The trapdoor closes, food goes by, trapdoor opens, then what?
I don't know.
Well, some people think it's like dropping a pebble down a well. It goes clunk down to your stomach.
No, it wouldn't work.
You don't think so?
No.
Well, as a matter of fact, you're right. That wouldn't work. But here's what does work. Here's a long balloon, and I'm put a marble in there. Okay, I want you to get the marble down to the bottom of the balloon. That's the food going down.
Oh, so you mean there's little things that push your food down?
Yes, not little fingers like yours, but little muscles that push it down like that. Now get the food back up.
I've never heard of food going up.
Well, yours is going to in just a moment, because the only time that really would happen is if you were upside down.
Yeah,
Then your food would go up.
that's
Okay, that's
true.
what I want you to do. Here's a little piece of apple, and I'll bring a couple of other ones over there. And I want you to go over there by the refrigerator and stand on your head. I know you can do it because I've seen you do cartwheels and everything else.
Yeah.
Okay, so go on over there, and you'll stand on your head. Okay, just put your feet up against the refrigerator here.
All right.
Okay, here's a little piece of apple. Chew it up and swallow it. Gone? There it
Yeah.
is. It's going down here, probably up to your stomach.
Right.
All right, it's gone. Here's another piece. Gone again?
Yep.
Good, I'll feed you the whole apple. You can stay right there. Jan, you shouldn't have been surprised because you've seen lots of astronauts floating around in their spaceships and they eat all the time.
Yeah.
And they're on their heads and on their sides and every which way. Okay, so you're our version of an astronaut. You're pretty strong for your age, right?
Yeah.
And then if I challenge you to crush an egg in your hand, would you accept the challenge?
Sure.
You right-handed or left-handed?
Right-handed.
Okay, give me your right hand. Here is one egg. Squeeze it into the bowl and break it. Can't do it, right?
You sure it's a real egg?
Yes, it is. In fact, go ahead, break it on the side. How would you ordinarily do it? Okay.
Oh, it is, too.
It's a real egg. Now, doesn't that seem strange that you weren't able to break it? Here, just put the whole thing in there. Most people can't. Even big, strong men can't break an egg by squeezing it in their hand. If you try it at home, they'll do it over the sink or in a bowl or something, because you might do it. And make sure you don't have a ring on.
Why?
Well, if you put the pressure on the egg all over it, like you did with your hand, then the egg is very, very strong. First of all, it's a strong shell. And then secondly, there's a liquid inside, and a liquid is very difficult to compress. And then third, it's a dome shape, which is also very strong. So don't have a ring on, because then you might put pressure on just one little tiny part. Well, here's another egg. You and I are going to really do a scientific experiment, more or less, to find out how strong an egg is. I have it in a little cup like that, and over there are some barbell weights. So you have 10 pounds over there, 2 5s, and I have 30 pounds over here. I want you to slowly and very carefully balance the barbell weights on top of the egg, but first, predict. We have a total of 40 pounds. Predict when the egg will break.
20 pounds?
Just a guess, right?
Okay, yeah.
I don't have any idea when it's going either. So let's see if it'll at least support 20 pounds.
Okay.
Slowly and carefully. Okay, 5 so far. Okay, add another 5. Don't drop it. Put it on very carefully. 10. Okay, take those 10 off carefully. I'll put on this 10. Okay, 5 more for a total of what?
15.
All right. Carefully, slowly. 15. Okay, add another 5. Here comes 20, which was your guess, right?
Right.
Okay, take your 5 off. Here comes another 10 for a total of 20. Okay, 5 coming up, 25. Whoop, did you hear what I heard?
Yeah.
Okay, go ahead.
I heard a crack.
I heard a crack. 25, go ahead. There we go. Well, you were pretty close, you were guessing. Total of, what was it, 25 altogether. It looks like you might have gone to 30, maybe.
Oh.
One crushed egg.